So, good afternoon, everyone, and welcome to the lecture. This is Capacitance lecture number 1, and we are at the beginning of the end of electrostatics. Once we are done with this, electrostatics as such is gone because we are not probably going to deal much with charges. So, this is the first of this type, and what I would suggest you is you have to do a lot of questions on this, which may not be possible for me to do in the class. So what I am going to propose you is you bring your favorite book in the class itself. I hope you understand what's the favorite book, right?
Yes, sir.
Yes, sir. So you bring that book in the class from today or tomorrow onwards, not maybe today, from tomorrow onwards, you bring that book. Everyone should have that book so that I can tell you which questions you have to do. I will try to put those questions on the screen as well. But if you have that book, it is easier for you to do it. What is going to matter here is the number of questions that you are going to do. Okay, so bring that book and I'll show you the page number and you can attempt that question so we can move along with questions faster than if I can do it pasting one by one and pasting one by two. So that would take a lot of time. But still, I will try to do that. But it would be easier if you can bring your favorite book in the class and I can tell you which page number am I talking about. Okay, having said that, this is the chapter on capacitance and what do you mean by capacitance? That is the first question that comes to your mind when we think about capacitance. Yes, what do we mean by capacitance? What do you understand by capacitance? Just give me a minute. Yes, so I was asking you, what do you mean by capacitance? Anyone has any idea? No idea. Get idea. Huh?
The amount of charge that can conduct.
Huh? The amount of what?
Charge, sir.
Capacitance of a conductor. We are talking about capacitance of a conductor. Let us first start with a conductor. Yes, what do you know about capacitance of a conductor? It is the hmm,
Amount of charge that can conduct through a conductor.
amount of charge that can conduct through a conductor. Do you understand what it means in the language of understanding? Okay, capacitance of a conductor is the measure of its ability. Capacitance of a conductor is the measure of its ability to store what? To store charge. That is how you will find the uh, you will find what you will find it written in books, but it's not a good way to understand this. Capacitance of a conductor is not the ability to store charge. In fact, it is the ability to store, that is a better word, energy, potential energy or energy. And this energy is stored in the form of what? This energy is stored in the form of what? A conductor can store charges. That's not a good way of saying it. A conductor can store energy. How it stores energy? By Akkar Vakkar Bombay wo abracadabra. Whoosh. Huh? How does it store energy? Hmm? How does it store energy? What type of energy stores? What type of energy stores? No idea?
Potential energy.
Which potential energy? Gravitational potential energy, spring potential energy.
Electro electrical part.
So it stores electrical energy. How does and where does it store that energy? Where? 4% of the universe is what we see. Does it store in that 4% or the 96% that we did not see? Where does it store? Where does it store? It stores energy in the form of electric field. It stores energy in the form of electric field. It stores energy in the form of electric field. And The good part is that electric field is not inside the conductor. That electric field is outside the conductor. So in the form of electric field outside the conductor, because there is no electric field inside the conductor. We've seen in the previous class that energy also. How much is the energy stored? How much energy stored? Let's see how many of you remember. How much energy stores? How do we find out that energy? How much energy is there? Let us suppose I am a conductor. How much energy am I storing? The energy stored per unit volume is how much? Huh? How much energy is stored per unit volume by this conductor? Conductor has charge. The charge creates electric field. The electric field is outside the conductor. Energy is stored. How much energy is stored? Does any one of you remember?
1/2 E square.
Huh?
1/2 epsilon naught E square.
God exists. I always start questioning the existence of God, but then you tell me answers like this, that God exists. Yes, God exists, and how epsilon naught E square is the energy that is stored by this conductor in a unit volume. Wherever there is a conductor, it will create electrostatic field, and it will store energy in that electrostatic field. How epsilon naught E square. So the ability of a conductor to store energy is known as the capacitance of this conductor. Okay, now how do you calculate the capacitance of this conductor? So you can write the next heading. Capacitance of an isolated conductor. Capacitance of an isolated conductor. How will I calculate the capacitance of an isolated conductor? Yes, any idea? Of n, and then I written conductors. My English is getting worse by each passing day. How do I calculate the capacitance of an isolated conductor? Yes. How do I calculate the
By
capacitance
potential.
of an isolated conductor? Huh?
By potential.
So I have this random shape conductor, and we have dealt with this random shape conductor a lot of times. And I gave a charge plus Q on this conductor. Where does the charge come? This is all solid, so all metal. Yes. Where does the charge come? Huh?
Where does the charge come?
We don't know where does the charge come. Hey Bhagwan. Whatever I do with you, everything goes down the drain of Hyderabad. So I am creating a lot of drainage problems for Hyderabad. It comes on the outer surface of the conductor. It comes on the outer surface of the conductor, and because of this charge, we have seen a lot of things. This charge creates electric field, and because of this electric field, this conductor also gets a potential of its own. It has been found by experimentation that this charge is directly proportional to the voltage V or potential V of the conductor. The charge that comes on the conductor is directly proportional to the voltage of this conductor or potential of this conductor. Or I can write Q is equal to CV, where C is a constant, proportionality constant. And this proportionality constant is known as what? Amitabh Bachchan. This proportionality constant is known as? It's not known as Amitabh Bachchan. It's known as the capacitance of this isolated conductor. So this is the only formula that you need to remember. Q is equal to CV, where C is the capacitance of this isolated conductor. And what is the definition? Now, the capacitance is the ability to store electrostatic potential energy in the form of electric field. How do I measure this capacitance? Or how do I measure this capacitance? Huh? How do I know, sir, I am measuring?
Farad.
How? How?
Faraday, sir.
By Faraday, sir. By not Faraday, sir, by finding out how much charge is required to change the potential of a conductor by 1 unit. How much charge is required to change the potential of this conductor by 1 unit. That is how I can measure its ability. Okay, so this is how I measure. Now, what type of quantity is capacitance? What type of quantity is capacitance? Scalar or vector? It is a scalar quantity. What is the SI unit of capacitance? Huh? SI unit is known as farad, not Faraday. SI unit is known as farad, or you can also call it coulomb per volt. SI unit is farad. You can also call it coulomb per volt. What is the dimension of this gentleman? You have to remember all these dimensions, because in the examination hall it might be difficult for you to get it in the required time. What is the dimension of this? Anyone can tell me the dimension? Anyone can tell me the dimension? M minus 1 L minus 2 ampere square T raised to the power of 4. This is the dimension of this gentleman. This is the dimension of this gentleman. Now, how much is 1 farad? All these questions are only for your academic purpose, for your board exams. So 1 farad would be the capacitance of a conductor which has 1 coulomb of charge and whose voltage is 1 volt. 1 farad may look like a very small unit, but it's actually a very big unit, and we will understand this very big unit. Anyways, this is how we begin the chapter on capacitance. Everyone has noted down up till now everything? Huh?
Minute, sir.
Yes. I know you need a minute. You need a minute. So you note it down. Till then, I will write the next heading. Noted it down? Noted down, everyone? Okay. Then the next heading that we will write is what are the factors that can affect the capacitance of a conductor? On what all factors that capacitance of a conductor depends on? Any idea on what all factor it depends on? No idea, sir. Get idea, sir. The first factor that it depends on is definitely size and shape. Depending on the size, shape, I would also like to add geometry. With shape comes geometry. If the conductor is spherical in shape, capacitance would be different. Cylindrical, capacitance would be different. Plain plate, capacitance would be different. So it depends on the size, shape, and geometry of the conductor. If obviously the size is big, the capacitance is going to be more. And if the size is less, the capacitance is going to be less. This point is clear with everyone? Huh? Yes or
Yes,
no?
sir.
Then the next factor which determines the capacitance of a conductor is the surrounding medium. What is surrounding it? Remember, it is why it depends on the surrounding medium, because it stores energy in the form of electrical field. electrostatic field. An electrostatic field depends on the surrounding medium. Epsilon naught, epsilon r. Do we remember that first class electrostatics? Huh? No one remembers it. Huh?
Yes, sir.
Half epsilon naught into epsilon r. I told you that is K. So it depends on the dielectric constant K. Dielectric constant. If you don't want to call it dielectric constant, you can also call it the relative permittivity of the medium. We remember that epsilon r.
Yes, sir.
Or it has gone above our saying bye 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 sir. I was for a lot of time I was in your head. Now I'm going. You did not utilize my potential, so I'm going. Okay, absolute permittivity or relative permittivity. Then it also depends, and which is a very important factor, presence of other conductors, and we will see how this presence of other conductors affect the capacitance of an isolated conductor. If this is an isolated conductor, and if I bring other conductors nearby it, the capacitance drastically changes. So these are the three factors on which the capacitance of an isolated conductor depends on. These are the three factors on which the capacitance depend on. Then there are other factors on which it does not depend on. Now these factors may be confusing at times, so you must remember. Have you noted down the two factors? Have you noted down?
Sir.
Okay, then we are ready to understand those factors on which the capacitance does not depend on. And what are the factors? It does not depend on the charge of the conductor. It does not depend on the potential of the conductor. And it also does not depend on the energy of the conductor. Now you may say, sir, Q is equal to CV. Q is equal to CV is the only formula we have read, and you had said that C is Q by V from this formula, so it should be directly proportional to the charge and inversely proportional to the voltage. No, that is not the case. That is how you just measure the capacitance. It does not depend on the charge. Capacitance is just the measure of the ability to store charge. How much charge it can store, that ability is capacitance. It does not depend on what charge is actually present on the conductor. We understand this?
Yes, sir.
Yes, sir.
So that is the first point that you must understand here. Capacitance of a conductor does not depend on the charge or its potential. It depends on the size, shape, and geometry of the conductor. It depends on the medium surrounding the conductor. It depends on the presence of other conductor, but it does not depend on the charge and the potential. Have you noted this down? Yes or no?
Yes, sir.
Then we move on to the next heading, and the next heading is capacitance. Everyone has noted this down now?
No, sir.
Capacitance of an isolated spherical conductor. Capacitance of an isolated spherical conductor. I will take you back to the previous slide since I've heard that you have not noted it down. So I'll give you time to note it down, and let me know once you are done. Then we move on to the next heading, and the next heading is capacitance of an isolated spherical conductor. Now, isolated spherical conductor also has capacitance, and we can calculate its capacitance. How will I calculate the capacitance of an isolated spherical conductor? So I have this spherical conductor, radius is r, and let me give it a charge q. And obviously, as you can see, all these stars are coming on the outer surface because the charge on a capacitor, charge on a conductor will only come on the outer surface of the conductor. Now, how are you going to calculate the capacitance of this conductor? We are assuming here that this conductor is surrounded by vacuum or simply air. We take vacuum and air as same. Yes. How do I find the capacitance of this conductor? And the answer is already known to you because I have told you what is the only formula that you need to remember in this chapter. I have told you that. Once you know that formula, the entire chapter is done. You don't have to do anything else. So now how will I calculate the capacitance of this conductor? Yes. Any idea? No idea. Get idea. I can't get idea because it is not no longer idea. It is Vodafone idea. Huh? Yes. How do I do it? Huh? Any idea? No idea, sir. I am new in this town. Yes?
Q by K, Q by R.
Q by K, Q by R. How did you get this? Q by K, Q by R. Huh?
Potential is K, Q by R.
Potential is K, Q by R. Right. The potential of this. And I will not call it now K. I will call it 1 by 4 pi epsilon naught Q by R. That was the potential of this. We have done that. Potential on the surface of the conductor is same as potential anywhere inside the conductor. So now I can write, see, this is nothing new. We already know it. Now I can write this Q as this 4 pi epsilon naught R times V. I can write this Q like this. Now, as soon as I write this Q like this, now it starts to appear in the same format in which I had written the definition of capacitance. Q is equal to CV. This, gentlemen, is a constant for a given conductor. This C becomes the capacitance of this isolated spherical conductor. So for an isolated spherical conductor, the capacitance becomes 4 pi epsilon naught into R. And whatever we have heard about capacitance is evident in this formula. R comes for the size, shape, and geometry. It was spherical, therefore 4 pi epsilon naught came. If it was of some other shape, something else would have come. This epsilon naught comes. This epsilon naught comes because of the surrounding medium. Since the medium was vacuum or air, therefore epsilon naught came. If it was something else would have come here. It also depends on the presence of other conductors, and we will see that in the next class, how it changes when other conductors comes in. But this is the capacitance of an isolated spherical conductor. Do we understand this, or this has gone above our head saying bye, 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 bye?
Understood, sir.
Now, now we can take the next step. Next step in evolution. What is the next step in evolution? Now, we have seen that to put the charge on this conductor, we have to bring charges from infinity and place on the surface of this conductor, and that work done is stored as energy. And how much was that self energy of this conductor? Anyone remembers it? Self energy of this conductor, you? How much was the self energy of this conductor? Anyone
K,
remember?
Q square by 2R, sir.
Okay, that means notes are helping you out, and go back and see. Okay, this tell fatafat. The potential energy of this conductor, U is always for energy. Potential energy of this conductor was K Q square by 2R. So I will now write it as Q square by 8 pi epsilon naught R. That was the self energy of this conductor. Now, as soon as I now see in the denominator 8 pi epsilon naught, something should click. What should click? That this can now be written as what? Akkar Bakkar Bombay wo. It can be written as Q square by 2C. So therefore, capacitance is the ability to store energy, not charge. Because energy of this gentleman depends on the capacitance. And that is the main concept of capacitance. Q square by 2C. Do we understand this? Or bye-bye?
Understood, sir.
So that means this capacitance is not a new chapter. We have already discussed the entire chapter previously. So we should move fast now. Now, instead of writing as Q square by 2C, the only formula that you know in capacitance, you can write this formula in 3 ways. What is the other way in which you can write the same formula? There's only one formula that you have to remember, which is new in capacitance. Q is equal to CV. 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 Huh? How can I write this another way? Huh? I don't know, sir. I'm new in the town, sir. Say, you can write it as half CV square. Just put Q is equal to CV and you will get it as half CV square. Or you can write it as half into Q into V. So this becomes the electrostatic potential energy or the energy stored in this conductor. But remember, this energy is not stored in the conductor, it is stored in the space surrounding the conductor. Dun, dun, dun. Do we understand this? Huh?
Yes, sir.
So this is the potential energy of the conductor. So and the ability to store this potential energy is known as the capacitance of this conductor. Now, moving ahead, we talked about what? We talked about Farad being a very large unit of capacitance. Now, before going into that, this is the capacitance of this conductor when the medium surrounding it is air or vacuum. Now, if this conductor is surrounded by a medium of dielectric constant K, if the conductor surrounding medium is a medium of dielectric constant K, what will be the capacitance? If it is surrounded by a medium of dielectric constant K, the capacitance will become abracadabra 4 pi epsilon naught into K into R. Is it clear to everyone?
Yes, sir.
So this will be the dielectric constant. And this dielectric constant is going to come a lot of time in this chapter, more than what it came in the previous chapter. Now we talked about the capacitance unit farad. Now comes a small task. Assuming Earth to be a uniform sphere conductor, the question is very simple. Calculate the capacitance of Earth. Calculate the capacitance of Earth. The radius of Earth, my dear friends, is 6,400 kilometers. Can you calculate the capacitance of Earth? You have 2 minutes to do this. Well, if I calculate the capacitance of Earth, it's a simple calculation. Capacitance of Earth will be 4 pi epsilon naught multiplied by radius of Earth. And what is the value of 4 pi epsilon naught? It's 1 by 9 into 10 raised to the power 9 into 6,400 kilometers, that is 10 raised to the power 3 meters. If I calculate this, the value that is going to come is 711 microfarad. This is how I remember it. It is 7.1 into 10 raised to the power minus 4, I guess. 711 microfarad, my dear friends, is the capacitance of the planet Earth on which we live. Now, to have a capacitor whose capacitance is 1 farad, you will have to have a sphere of radius 9 into 10 raised to the power 9, which is somewhere close to the radius of our lovely star, Sun. So, Sun would have a capacitance somewhere close to 1 farad. That means farad is a very, very huge unit. Even 711 microfarad is almost like infinite. We cannot create a capacitance equal to the capacitance of Earth. So normally in day-to-day life, the capacitance that we will encounter will be in the order of picofarads and nanofarads, not even in microfarads, because even microfarad is very big. Do we understand this? Yes or no?
Yes,
So this
sir.
is just to make you understand that farad is a very, very huge unit. It may not look like one, but it is a very, very huge unit. Taking taking the process further, I think in the last class we had discussed sharing of charges. Did we discuss the sharing of charges in the last class?
Sir.
Yes. Now we can again go back to that sharing of charges thing and probably understand them in a different way. Now, what do you mean by sharing of charges? I have seen a lot of questions come on this, so I will have to give you this one again, and this time I think you will be able to make more sense of it and try to understand it in a different light as well. The heading is sharing of charges. Now, what is sharing of charges? There have been questions on JEE about this lot of time. Sharing of charges. Now, you have two conductors and we have just taken them as two spherical conductors. Q1, C1, V1 and U1 is the charge, capacitance and other things for conductor number 1. Q2, C2, V2 and U2 is the charge on the other conductor. Now what we are going to do is we are going to connect these two conductors. Then they get final charge Q1 dash, capacitance remains same, their voltage becomes same. Do we understand this? So whenever you connect two conductors, they will come to the same potential. We understand this? Yes or no?
Sir.
Their energies are also going to change. The only thing that are going to remain constant is the capacitance, because capacitance does not depend on the voltage. Yes or no? In the initial case, you can write the charge on the conductor as C1 into V1. In the final case, you can write the charge on the conductor as C1 into V and the charge on the other conductor as C2 into V. Do we understand this? We have already seen how we are going to solve this question, but again, now we will see in this new light that we know that 1 by 4 pi epsilon naught into R is actually the capacitance of this conductor. So the first thing that you must remember is total charge will remain constant. So Q1 plus Q2, initial charge, shall be equal to Q1 dash plus Q2 dash. We all understand this, and that will be equal to the total charge Q. Yes or no?
Yes, sir.
And the second thing that you understand is how will the charge be divided? Q1 dash by Q2 dash will be equal to R1 by R2. And now you know this R1 by R2 is also equal to C1 by C2. Yes or no?
Yes, sir.
So now you can write this revolutionary formula that this Q1 dash will be equal to total charge Q into C1 divided by C1 plus C2. Yes or no? We can write it in this form. Or you can write it in this form, Q into R1 divided by R1 plus R2. Are we able to understand this? Yes or no?
Yes, sir.
Similarly, you can write Q2 dash as total charge Q into C2 divided by C1 plus C2, or you can write it as total charge Q into R2 divided by R1 plus R2. They will reach a common potential. They will reach a common potential. I think we had seen the formula of that common potential in the previous class. Again, we can write this formula of common potential in this class, you can write this formula as total charge Q divided by C1 plus C2. Or you can also write it as C1 V1 plus C2 V2 divided by C1 plus C2. Do we understand this? How we are writing all these things? Yes or no?
Yes, sir.
Now, whenever you connect these two conductors by a wire, some energy is lost in the form of heat. So, energy lost in the form of heat, or you can write the heat energy developed in this connection process. How will you find this heat energy? You will find the total initial energy, you will find the total final energy, and the difference in this would be equal to the heat energy uh, that has been dissipated in this process. Remember, the initial energy will always be more than the final energy. Do we understand this? Now you can
Yes,
find
sir.
the initial energy, you can find the final energy, and then you can take the subtraction, or you can remember this formula, and with this formula you should be able to get the answer for this type of connection very quickly. C1 C2 upon C1 minus C2 into V1 minus V2 the whole square. That will be the energy lost in the form of heat in such a connection. Do we understand this? Remember these formulae, remember these shortcuts, because a lot of time questions have come on this. So you should not be found wanting on this small thing. Anyone has noted this down?
Yes, sir.
Because this heat energy which is coming out is going to come almost throughout the chapter. So this is the first case in which you will have to find out this heat energy which has been lost. Are we ready for the question? Eh?
Yeah.
Okay, comes this question, question number 1. Two insulated metallic spheres, 3 microfarad and 5 microfarad, are charged to 300 and 500 volts respectively. The energy loss when they are connected by a wire is, and you have 2 minutes to show me your talents. Option D is what I am getting from the students, and option D is wrong. Option C is the correct one. So you must be wary about the units, my dear friends, and if you don't worry about the units, you will end up with such a thing. What you had to do was the energy loss in the form of heat is C1 C2 upon 2 times C1 plus C2. Remember, C1 and C2 are in microfarads, my dear friends, multiplied by V1 minus V2 whole square. I don't think I will have to put the values and calculate and give you the answer. The answer is 0.0375. That is what I can tell you, and I am not going to calculate it for you, right? Because you know my calculations are very bad. So I will leave it for you to calculate. If you can't calculate it correctly, well, you can use a calculator to do the same. Okay. Let me move on to the next question. Shall we move ahead in life?
Yes, sir.
Okay, please be careful that whenever you have capacitance, you have microfarad and nanofarad and picofarad. So be very careful about those units that are coming. And this is the next one in line. A and B are two isolated conductors. That means they are placed at a very large distance from each other. When they are joined by a conducting wire, find out all these things that you have to find out. You have exactly 2 minutes to give the answer for this one. Best of luck. Final charges on A and B. Any answers? Okay, it looks like you have been trapped in this question. Anyways, I will give you this question as a homework, and we will discuss the answer in the next class. There is nothing very dramatic about this question. It's a straightforward question. I'll give you time to go back and see what all things we have done. Go through the formula once again, and then we will come back on this question in the next class. Everyone has understood what we have done today? Okay, then we'll come back to this question in the next class. Don't worry. We have got enough time that we can spend. So take care. I'll see you in the next class. God bless all of you. Bye bye.